Now I'm going to move on in the interest of time to another example and a different type of coupling, which we can of course use to boost simulation capabilities. Now this is a coupling with Ansys Motion. So Ansys Motion is a multi-body dynamic solver, which is used to analyze systems of interconnected bodies. So this type of coupling essentially addresses some of the limitations of the embedded motion solver that I mentioned beforehand, and it introduces some new functionality. So through this coupling, users can again prescribe complex motion profiles, but this time consider geometry to geometry interactions. So connections, joints, springs, and so on. Motions can also be driven instead by applied forces rather than just a constant velocity or acceleration as it is in Rocky. So if we take the backhoe loader, for example, it would actually be possible to simulate the bucket stalling based on the resistance by the bulk. And we'll also see that we can analyze deformations and stresses of flexible bodies. So this coupling is essentially executed through an FMU. Now, this FMU file includes all of the necessary information to describe the geometries themselves, as well as their motions. And so it's essentially, we can create a feedback loop here where the FMU file or the Ansys motion solver will output the movements, the displacements, rotations, and so on of the geometries, and Rocky will feed back the forces and moments calculated through the interactions between the bulk material and the geometries. So because Ansys Motion, or the Ansys Motion Solver, is included in the FMU file, it's not actually a requirement for both Motion and Rocky to be installed on the same machine, but you still need a valid Ansys license to actually run the solver. So if we consider this scenario where we're just looking at the rear bucket assembly on this backhoe loader, now we can include the actuators and the transfer of force through the joints. So in this model, displacements have been prescribed using equations which describe the motion profile. And you'll notice actually that the arm this time has a smooth displacement profile. And we'll soon see this directly and the effects of this on the bulk by comparing against 4 different cases. So we'll compare against a Rocky standalone case, an Ansys motion case, two types of Ansys motion cases where we have rigid bodies, but one where the actual base is mounted with a bushing joint. And the 4th case is a special one where the boom and the arm are treated as flexible bodies. And so what we can see here as we compare between these cases is that, of course, with the Ansys motion coupling, the movements are much more smoothed and realistic compared to the very jagged motion or the very jagged behavior in the Rocky standalone cases. This is because direction changes are effectively instant in the Rocky case. Now, as a result of this, the mass collected is different between these configurations. There's less mass in the Rocky result due to the abrupt motion transitions, effectively causing material to be thrown out of the bucket. So the flexible body case is a special one. We play those back. And this is because of course, the resulting stresses and deformations can be calculated in real time in motion, but these flexible bodies don't actually interact with particles in Rocky. So that's just one limitation of the current implementation. Now, of course, the reaction loads on the structure will be different between these cases, and we can see the reactions, for example, with the bushing joint model are smaller than those with fully fixed bases. Now, I thought it might be worthwhile to note that as an upcoming feature release in 24 R2, the ability to prescribe custom motion frames, which are defined by CSV and Excel files, will be added as will be available now for users to essentially describe motion, or a custom motion profile. So this one's coming up in the next release